Good morning, everyone. Everyone can hear me? All right. My name is Ahmad, and today I will tell you about how user tracking data moves in the online advertising ecosystem. This work is done with my advisor, Krista Wilson at Northeastern University. So let's get into it. We know that when a user goes online and starts browsing the web, this information is known by multiple third parties. For example, in the case of CNN, there could be third parties such as DoubleClick and Facebook present on the website, which sees that information. And as the user browses more websites, it essentially exposes itself to more and more third-party trackers. But we know this. We can actually visualize this information in a browser using an extension like Lightbeam. However, this picture is missing something. It does not take into account the information sharing between these third parties due to cookie matching and real-time bidding. And the modern advertising ecosystem is moving more and more towards real-time bidding, where a user goes online on a publisher where there is some content and a space to show ad. And this publisher is running a JavaScript from these special ad networks called supply-side platform. And the role of these supply-side platforms is to work closely with the publishers to maximize their revenue by forwarding the ad request to the most lucrative ad exchange. Let's say, in this case, to DoubleClick. And the job of the exchange is to solicit bids from its demand-side platforms, which are, again, very specialized ad networks, which work closely with the advertisers, such as Nike and Coca-Cola, and they bid on behalf of them. And depending on the information they have about the user, they will bid high or low, and someone will win the auction and reserve the right to serve user the ad. Let's say in this case, Criteo wins the auction and serve the user an ad from Nike. The key thing to notice over here is that although Right Media does not win the auction, it still sees the impression because of its participation in real-time bidding. So the process of serving this ad could look like this: from CNN to Rubicon to DoubleClick to Criteo. And the missing link is Right Media. And we take this information into account and we adjust the picture I showed you earlier on. We take into account these missing information, missing links, which basically account for the information sharing. So you can see that even though companies like AppNexus is not present on CNN, it still sees the impression from CNN due to its participation in real-time bidding. And DoubleClick was not present on Amazon, but still sees the impression from Amazon. So the goal of our study is to model the diffusion of impressions in the advertising ecosystem. In particular, we want to take into account real-time bidding effect into this ecosystem. And we want to answer the following questions. One, what fraction of user impressions are viewed by ad companies? And second, how much blocking extensions help at protecting users' privacy? And throughout the talk, I will be using and throwing some terms at you. By impressions, I mean page visits. Publishers are for first-party websites, user explicitly visits. And by ANA domains, I mean advertising and analytics-related companies such as DoubleClick and Criteo. So in the rest of the talk, first I will tell you what data set we use for this study, and then I will tell you how we conduct our simulations using this data set. I will show you then some results, and towards the end, we will discuss how effective blocking extensions are at protecting users' privacy. So for this study, we used data from our prior work where we trained personas using more than 700 popular e-commerce websites and then solicit retargeted ads through top 150 publishers. You can read the paper if you are interested in the details, but the key takeaway is that we have inclusion chains for all resources. One of the example chain I showed you earlier on is serving this particular ad from CNN to Rubicon to DoubleClick to Criteo. And we have all these inclusion chains for all the resources. And we build a graph out of these chains. So take into account these two chains where CNN and Amazon are publishers and the rest of them are ANA domains. So the graph could look like this. The user visits Amazon and then Pragmatic, DoubleClick, and Criteo. And along the edge, we also encode the weight information, which essentially means how many times party 1 sends a request to party 2. And then when the user visits CNN, this information will be integrated into the graph as well. And you can see the weight along these edges. Do notice that the weight along double-click to Criteo now increases to 2 because this is the second time double-click is sending a request to Criteo. So in this graph representation, the nodes are publishers and ANA domains, and the edges are publisher or ANA, publisher to ANA or between ANA domains themselves. In total, we have roughly 1,900 nodes, out of which 1,000 are ANA domains, and we have roughly 26,000 edges, out of which a majority are between ANA domains themselves. I don't have time to go into the detail of this graph, but I will give you some highlights. The graph is very dense. We did not find any distinct communities in the graph. For example, we ran community clustering algorithms, and we could not find distinct groups of supply-side platforms and demand-side platforms. So which means that the graph is very interdependent. We did run PageRank and between the centrality on the graph, and we got expected top nodes like DoubleClick, Facebook, etc. So again, to reiterate, the goal of the study is to model the diffusion of impressions in the advertising ecosystem. And to that end, we run simulations. In particular, we simulate browsing traces for 200 users, where each user generates an impression on n selected publishers from top Alexa websites. And these impressions are forwarded to ANA domains through two methods. One, direct propagation, where an ANA domain receives the impression because it was directly embedded into the publisher website, or it participated into the RTB auction and won the auction. And notice that we can observe this information because it goes through the user browser. The second way is indirect propagation, where an ANA domain sees the impression because it just participated in the RTB auction, although it never won the auction. And again, I will go back to that the chain example. And in this case, Rubicon, DoubleClick, and Criteo observed the impression through direct propagation because they were either on the website or won the RTB auction. And Right Media did not win the auction, but still saw the impression because of its participation in the RTB process. And one more thing I would like to highlight is that winner of the auction in our simulations is determined by the probability density function of the outgoing, of the weights of the outgoing edges. So let's take a detailed look into this. Consider this example graph where there are two publishers, P1 and P2, denoted by blue circles, and the rest of them are ANA domains, which are advertisers and DSPs bidding on user behalf, on advertisers' behalf. And I distinguish exchanges with red circles, and the job of the exchange is to solicit bids, but it can also forward indirect impressions. So if a node is directly activated, it will have a solid boundary. If it gets an impression through indirect propagation, it will have a dotted boundary. And in this particular simulation, we manually select 37 exchanges, 37 nodes as ad exchanges to forward indirect impressions. So the simulation would look like this. The user visits P1, where it contacted E1, and E1 places bids, asks for bids from its partners A1 and A2. Now notice that there is the weight on these edges, 10 and 90. And because of higher weight towards A2, it is more likely to win the auction, and it does. Hence it has a solid boundary. But notice that A1 also observes this impression because it got the bidding request, a bid request from E1. E2 then further sells this impression to A5, but the key thing to notice over here is that A4, although there is an edge towards A4, A4 never got the impression because A2 is not in our selected list of ad exchanges. Next, the user visits P2, where it contacts E2, and E2 again asks its partners to place bids. And again, A2 wins the auction, so the impression counts increase for A2. A3 observes the impression through indirect propagation, and then A2 further sells the impression to A5. So this is how the simulation progresses. So that was one of the simulations I showed you from our paper. We have two more. So RTB relaxed, where we assume all ANA nodes are ad exchanges. Now, this is a loose assumption. Hence, this model provides an upper bound estimate on the impressions observed. The second one is cookie matching, where indirect impressions are forwarded only along 200 cookie matching partners. So essentially, out of 26,000 edges, the indirect impressions are forwarded only along 200 edges. And this provides a lower bound estimate. And we think RTB constraint, for which I showed you this slide earlier on, is a more realistic scenario, where we manually select 37 nodes to serve as an ad exchange and forward indirect impressions. So on this graph, on the x-axis, I show you fraction of impressions observed, and on the y-axis, I show you the fraction of ANA domains observing these impressions. So you can see that the blue line and the green line are the upper bound estimates and the lower bound estimates respectively, and the red line in between is the realistic scenario of RTB constraint, for which I showed you the slides earlier on. And the key takeaway is that RTB constraint is very close to RTB relaxed, although we selected only 37 nodes to serve as ad exchanges. And in particular, 10% ANA domains see more than 90% of ad impressions in real time in RTB constraint. So now that we know that under RTB a lot of impressions get leaked, the next question we want to answer is how effective blocking extensions are at protecting users' privacy. In this slide, I show you the same behavior I showed you in the earlier slide, but let's assume that now the user has installed an ad blocking extension in which all outgoing requests to double-click, OpenX, and PubMatic are blocked. Now when the user visits CNN, the third parties view this information, but since there is ad blocking extension installed, the outgoing requests to PubMatic, OpenX, and DoubleClick will be blocked. However, due to their participation in RTB and close collaboration, this information will move along from Facebook to OpenX to Criteo and so on. And you can see that all the DoubleClick and OpenX should not have seen this impression because of the blocking extension. They still do because of their participation in the real-time bidding process. And in this slide, I show the impressions observed under various blocking scenarios by these advertising domains. So we see that disconnect is the most effective. And whereas AdBlock Plus has no effect at all. And the reason is AdBlock Plus is enrolled in acceptable ads program where they whitelist majority of the popular domains. So the key takeaway again is that due to RTB, impressions gets leaked to major ANA companies even with blocking extensions installed. And in this slide, I show you top 10 domains which sees the impressions under various blocking scenarios. So we see that AdBlock Plus has no effect at all. It is no better than no blocking, where it sees more than 90% of the impressions. Whereas disconnect is the most effective, but still more than 50% of the impressions get leaked. Under EasyList, there are no impressions leaked because in our methodology, we detect ANA domains based on EasyList criteria. So by that, they won't see any impressions. And this table shows the top 10 domains under AdBlock Plus, which sees the most impressions. So you can see that major domains like Google Analytics and BlueKai, Criteo are present over there, but some interesting ones such as Pinterest are also present, which sees more than 90% of the impressions because they are embedded in more than 150 publishers. Before I conclude, I want to mention that there are certain limitations in our simulations. Our simulation provide approximations because different users might have different browsing behaviors, and we conduct simulations based on only top publishers. The ecosystem could have changed dramatically since we last collected the dataset, which was in December 2015, and these simulations are not representative of the mobile advertising ecosystem. And in summary, we are the first to provide a model to study the impact of real-time bidding on users' privacy. We run simulations to see that more than 10% of ANA companies, ANA domains view more than 90% of the impressions under realistic scenarios. And we also saw that even with blocking extensions installed, a majority of user impressions are leaked to ANA domains. In particular, AdBlock Plus is not effective at all because of its participation in the acceptable ads program. Our data set and code is present on this link. And with that, I'm happy to take questions. Thank you very much.
Any questions for the speaker?
I'm wondering, when you say leakage, what exactly is being leaked, especially on the server-to-server requests? Because it's possible that an exchange is actually potentially cookie, especially if like the participating bidder maybe isn't allowed to receive that cookie, especially as GDPR is coming out. There's more GDPR consent tokens coming in, and exchanges that are abiding by those might not be exposing the user's cookie or even the user's IP address to the participating DSP, and therefore the DSP will receive the impression, but the DSP is not necessarily receiving any user information. So I'm wondering sort of like how you would classify leakage and how you could potentially like enhance your data set to get insights into like whether or not user privacy is being violated on these server-to-server requests.
Yeah, I think that's a great question. We haven't looked into these particular details like in the effect of GDPR and particular PIIs. When I say information leakage, I am talking about impressions leaked, and in particular, I mean page visits, like CNN. We did not look in specific like whether like the username is being leaked or like email address is being leaked, but that's a very interesting avenue, and we should explore that definitely.
So we just heard another talk where people were training up things to sort of not just have a simple list. And I realize you haven't already done analysis based on the talk you just heard, but I was wondering if you might speculate about how that might impact the leakage that's going on if you're using something that's smarter like
Yes.
that.
So that's again a very great question. I showed in one of the slides that when I was showing the top 10 companies, that easy list we don't see, because by default our detection methodology is easy list. But if you're using something like uBlock Plus or NoScript, it's even more effective. But again, I would like to show one slide over here. So we also selected only 5. Where in our simulation where I said we select 37 exchanges, we also run with various different exchanges. So you can see that even with 5 exchanges, a lot of information is leaked. So even if like those 5 big players are present, they can still leak that information, because the advertising ecosystem is so dense. Like if some of them see this information, the information gets propagated very quickly.
Any more questions? To follow up on the first question, what exactly does an impression typically look like? Like, I mean, you said you're not sure, but like, what are these things?
So we just say that page visit, but essentially when a request goes from an ad exchange to a demand-side platform, it would tell a lot of other things. For sure, cookie as well, because demand-side platform has to identify the user to place bid effectively, and that request could entail other information as well. For example, the website. It could also, I mean, other researchers have shown that sometimes like more PII is even leaked. So we haven't looked at in particular details, but for sure that can also get leaked.
Thanks.
Yeah.
All right. Thank you.